Hi there. In the previous two videos, we started talking about complex numbers and gave some motivation on how to think about them, with the other numbers that we're more familiar with. So one of the things we still need to justify is that why is a complex number or an object that we define as a complex number is indeed a number. And so let's just recall what we did last time. So let's say we have an object of the form a plus ib. We called this object as a complex number. So it has a real part, which is this. So that's the real part of the complex number, real part. And it has an imaginary part, which carries with it the symbol I. Now, so let's just write this as an imaginary part for now. Now, why is this object called complex? It's because it has these two components, a real part and an imaginary part. However, I here is to be taken more as a unit in the imaginary, let's say, direction. Now, it's not at all obvious from this particular definition how to think about complex objects of this form somewhat more pictorially. That will make it clearer how to make a separation between the real and imaginary parts, but we'll get to that very soon. We'll give a more geometric interpretation of what complex numbers are. But for now, what we'll do is we'll take this sort of symbol I along with us in some of the algebraic manipulations that we do. And what we'll say is that I denotes some kind of a unit which helps us identify a real part and an imaginary part, but the imaginary part itself is actually the real number b that is that sort of gets attached with the symbol I. So somewhat more precisely, if you're asked like what is the real part of z, we'll say that the real part of z is simply the real number a, which doesn't carry with it the symbol I in this case, and the imaginary part of z is the real number b. So notice that a and b are both real. So a, b are real numbers. Okay, so I is simply a symbol or a unit that helps us identify the imaginary part in this complex object, and the imaginary part itself is actually the real number b, and the real part is the real number a. Okay. Now, one of the things that we'll do here is that we'll sort of now try and introduce or make some definitions of how to carry out algebra with these complex numbers, in the sense that we'll now define addition, subtraction, multiplication, and division of complex numbers. There are certain sort of steps in that definition that will assume that will make assumptions about how we work with the symbol I, and these are assumptions in the sense that we won't be able to justify them from first principles, but what we'll claim is that if we accept these definitions for addition, subtraction, multiplication, and division of complex numbers, then complex numbers or these complex objects follow all the rules that we established or that we chose to identify any kind of number with. So given an object, if that object satisfies the set of rules we listed out in the previous videos, we'll choose to call such objects as numbers. So with the definitions that we'll make, it turns out that these complex objects will satisfy all those rules, and therefore we are calling such a complex object as a complex number. So let's just work out how that works, and it will make it clear where some of the assumptions are, where some of the assumptions that we're making enter the picture. So just to recap here, the real part is the real number a, and the imaginary part is the real number b, and I sort of helps us identify the imaginary part in this complex object. All right. So now let's see how do we define the addition of complex numbers. So let's start with addition and subtraction of complex numbers. So let's say we're given one complex number z1, which is again of the form a plus ib, and another complex number z2, which is of the form c plus id. Then the way we define the addition of complex numbers is that the sum z1 plus z2 is a plus ib plus c plus id. Okay, and then what we'll do is we can sum, we again have something that carries, we have an a and a c, which are both real numbers, so we can simply add them. So we have a plus c. And then we'll identify the symbol I in this expression. So we have two expressions that carry the symbol I, IB and ID. And what we'll do is we'll combine these two together. So we'll write this as I times B plus D. Okay. And notice what happens if we make this definition for addition of complex numbers. What happens is that we again have an object that looks like it has a real part, which is a plus z, so that's a real part, which is the sum of two real numbers, so a plus c is also a real number. And then it has an imaginary part, which is b plus d, and b and d are both real numbers, so this is also a real number, so this is the imaginary part. And therefore this composite object also looks like what we define as a complex number, which is it has a real part plus I times an imaginary part. And therefore what happens is if we make this definition, then z1 plus z2 gives us another complex number. And because of the fact that real numbers commute, we find that z1 plus z2 is also equal to z2 plus z1, because z2 plus z1 will give us c plus a plus I times d plus b. Right? So, sorry. Let's just write this as z1 plus z2, and this is z2 plus z1. And because real numbers commute, we find that z1 plus z2 is actually equal to z2 plus z1, because a plus c is equal to c plus a, and b plus d equals d plus b. And so with this definition of complex numbers, we'll find that z1 plus z2 is actually equal to z2 plus z1, which is one of the rules with which we if an object satisfies, this was one of the rules that the object needs to satisfy for it to be called a number, and this rule is again called that addition is commutative. So again we'll say that given this definition of complex numbers, their addition is commutative. All right, now in the same way we can carry out subtraction of complex numbers, and what we'll do is, so we need to define z1 minus z2. So if this is z1, this is z2, then z1 minus z2 is a plus ib minus c plus id. And again we can combine the real and imaginary parts, so this will give us a minus c plus I times b minus d, and that's z1 minus z2. And again this composite object looks like another complex object because it has a real part plus I times an imaginary part, so this is another complex number. Okay, great. So the next step is to define multiplication of complex numbers. Actually before doing that, there's one important point, which is well, given this given a complex number, let's say z1, which is a plus ib, or z2 c plus id, they are equal to, we'll say that this is equal to c plus d times I, and this is equal to a plus b times I. So it doesn't matter on which side of the real number b we write a. Now this is not at all obvious. What we are claiming here is that the symbol I, which is the unit imaginary number, commutes with any real number it appears with. So this we'll take to be sort of a definition that given a symbol I, we can sort of move it around the real numbers that it's coming along with. Okay, so with this sort of definition, let's define multiplication of complex numbers. Z1 times Z2 is A plus IB times C plus ID. And actually this rule is not sort of, this rule, or rather multiplication is sort of a generalization of this definition. So now what we'll do is we'll say that, okay, we know that real numbers distributes, multiplication of real numbers distributes over addition, and in making this definition of multiplication of complex numbers, we'll say that I sort of carries along as a symbol for a unit imaginary number, but it doesn't change, or we are still allowed to use the property that if we are multiplying A with C plus I. So for instance, in this case, what we'll claim is that we can write this product as A times C plus ID plus IB times C plus ID. So we are working with the symbol I as if we are working with any other number, like the real number that we are familiar with. So we're still claiming that, okay, A and this sort of composite sum, A plus IB, can and its product with C plus ID can be written in the form A times C plus ID plus IB times C plus ID. So this is part of the definition that we're making for multiplication of complex numbers. It's not at all a first principle derivation of why we are allowed to, so for instance, commute I with B, and why we are allowed to why we are justified in picking out this IB and writing it as or multiplying this with C plus ID and then distributing this product over addition, as we'll do in the next step. So these are not first principle derivations. This is just a definition of multiplication, and we'll give it a more geometric meaning in subsequent videos. So given this definition, what we'll say is we can distribute this multiplication over addition. So this gives us A times C plus, again, we'll allow I to commute with the real numbers that it's operating with. So we have I times AD. So we could have written I anywhere in this expression. So just for simplicity, I'm writing it as the first symbol. So I times AD. And then we have I times BC plus I times B times D. Okay. So again, we'll do the same thing as we did in when we were adding complex numbers, is to identify in this expression the real numbers and the expression that appear with the symbol I. Now notice that here we have an I square, or an I times I, and we know that I square is minus of 1, and minus 1 is a real number. So this I times I is actually minus of 1, and therefore we can combine it with A times C to write this as A times C minus B times D plus, now these two carry a single unit I, and so we can write this I times AD plus BC. Okay, so with this definition of multiplication, what we find is that the end result is another sort of object that looks like a complex number, because we have a real part, which is AC minus BD, plus I times an imaginary part, AD plus BC, right? And these two parts are both real. So this sort of object is another complex number. And likewise, we can check that this Z1, Z2, with this definition of multiplication, Z1, Z2 is actually equal to Z2 times Z1. So it turns out that if we make this definition, then this definition for multiplication of complex numbers, then multiplication of complex numbers also commutes. So that's something that one should check. So this will turn out to be equal to Z2 times Z1. Okay. And the last step is to define division of complex numbers. So Z1, let's say, divided by Z2, provided Z2 is non-zero. So what does it mean for a complex number to be non-zero? A complex number is, actually let's do that first. Two complex numbers are equal to each other. So Z1 is equal to Z2 if their real parts are equal and their imaginary parts are equal. So if real part of Z1 is equal to the real part of Z2, and the imaginary part of Z1 is equal to the imaginary part of Z2. So in this case, these two complex numbers are equal if A equals C and B equals D. So a complex number is 0. Let's say Z with z, or in this case, let's pick out z2. So z2 is 0 if, so 0 has only a real part, which is 0, if c is 0, and, or we can input, in fact, we can write this as 0 times I times 0. So if c is 0 and d is 0. So complex number is 0 if both its real part is identically 0 and its imaginary part is identically equal to 0. Okay, so if z2 is non-zero, we can divide z1 by z2 and write it as a plus ib divided by c plus id. Now again, what our aim is to write this sort of expression in a form of a real part plus I times an imaginary part. So we need somehow to get rid of the I in the denominator here, and one way to do that is to multiply the numerator and denominator with c minus I times d. And again, we are saying that z2 is non-zero, so that's important. So again, we can carry out the product in the numerator and the denominator. So in the numerator, we'll find this is AC minus I times AD plus I times BC minus I times BD. And in the denominator, we have C times C, which is C square, minus I times C times D plus I times D times C minus I times D square. Now again, the real numbers sort of commute, so this minus I times CD is actually equal to I times DC, so this cancels out. And in the numerator, we have an I square here, which is minus of 1. So overall, we have a plus sign here because this is minus gives us a plus. So we have AC plus BD. In the denominator, we also have an I square, which will give us a minus 1. And then we have C square plus D square. Okay, so that's one of the parts, which is the real part, and then we have an imaginary part, which is I times BC minus AD divided by C square plus D square. Okay, so this is how we sort of define division for complex numbers. So these are the four basic operations. And again, we can also check what happens if we carry out an expression of the form. So again, there are two important things to check, which will be a good exercise. So for instance, z1 times z2 is actually equal to z2 times z1, and we can check what happens if we have an expression of the form z1 times z2 plus z3 is indeed equal to z1 times z2 plus z1 times z3. So given these definitions for addition, subtraction, multiplication, and division, we'll find that these complex objects satisfies all the rules that we associate with numbers, and that is the reason we call these objects as complex numbers. However, it turned out that given all this, historically at least, given all this, people were still sort of skeptical of what this I is and why is it that this algebra is justified and why is it that it has any meaning. And that is where a very pioneering work by Wessel and Argand really gave complex numbers, the study of complex numbers, a boost, which is when they gave complex numbers a more geometric meaning. So our attempt in the next part of the video will be to give these complex numbers a more geometric meaning, and then we'll see what addition and multiplication actually means geometrically, and that will sort of give us more of an intuition of what these numbers really mean. So see you in the next part. Thanks.